Yeah. Did you do the train? Okay, oh, Victoria. I did cruise out. Oh, it's our Victoria.
All right, I'll get started. Let me begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you just bless our work today. Help us to glorify you what we do. And I just pray that the students, if they're struggling, that they would just be encouraged to continue on and just to do their best, Lord, each day, Lord. In your name I pray, Lord Jesus. Amen.
Amen.
All right, so let me tell you guys about the, I don't know what you want to call this. You could call it the division algorithm, I suppose. And so this is just more or less a summary. This is a summary of the idea that we had last time, which was long division, okay? So like given polynomials f of x and g of x, there are polynomials p of x and r of x such that the degree of p of x is actually equal to the degree of f of x minus the degree of g of x, and the degree of r of x is less than the degree of g of x. And I mean, here's what happened. F of x over f of x over g of x is equal to p of x plus r of x over g of x. And let me just introduce some language for you guys. This kind of thing is what I would call a proper rational function. And by that, I simply mean that the degree of the numerator is strictly smaller than the degree of the denominator. All right? So graphing proper rational functions is like the easiest kind of graph of a rational function that we can come across. So we'll talk more about that as we go on. But let me give you another example of long division before we get further. So like example 1. Example 1. I will do something rather silly. I'll divide x squared, well, not x squared, let's divide x plus 1, all right, into x to the 4th plus 3, all right? Let's try this out. So to start with, what do I put? I put
x3, x cubed.
X cubed, Michael's got it. So that brings down x to the 4th
X plus 1.
plus x cubed. Then I subtract. And I get myself minus x cubed plus 3. All right, so what's up next? Well, to get rid of this minus x cubed, I need a minus x squared. That brings down minus x squared. Minus x squared, excuse me, minus x cubed, minus x squared. Then we take the difference there. What's that get us? Looks like we got a x squared.
X squared
Plus
3.
plus 3. Very good. Now how do I want to get rid of x squared, so I need to do what? Plus plus x up here. All right. Now x times x plus 1 is x squared plus x. So I subtract, and I get minus x plus 3, right? I'm going to go back to black again. How do I get rid of that minus x? What do I do?
Add.
Add. Okay, so how about minus 1? Minus 1, right? That's going to give me minus x minus 1. I take,
X squared.
well, not x squared, but I subtract them. And 3 minus a minus 1 gives me 4. 4 is the remainder because that's a smaller degree than x plus 1. All right? So what does this calculation mean? This calculation...
It is x cubed minus x squared plus x minus 1 times x plus 1 plus with a remainder of plus 4.
Yes. All right. So what this means is x to the 4 plus 3 divided by x plus 1.
Oh, sorry.
Is
Different form.
Okay, Michael, you're going to have to raise your hand if you got a question, okay? X to the 4th plus 3 divided by x plus 1 is equal to x cubed minus x squared plus x minus 1 plus 4 divided by x plus 1. So that's what this long division means. All right?
Hold on.
So in this case, this piece right here is the p of x, all right? The r of x in this case is equal to 4, and this right here was my f of x, right? And this was my g of x, if you're trying to match up this example with the general algorithm that I was just writing down, okay? There's one homework problem that's like this, I think problem 59. I ask you to find p of x and r of x such that this is all happening. All I'm asking you to do there is to do long division and interpret it. All right? Any questions? Yeah.
Could you go over signage and the long division again? Like I'm looking through it as
Signage?
each term gets to like x to the third factored with x plus 1. It's mostly just plus x and minus 1. I was thinking, because that would be what cancels out the plus 3 to get us 4, right? I know that we're trying to cancel x, so it's minus negative x. And is that why we factor positive x there with x plus 1?
I'm not sure you're saying factor. I'm not sure what you mean by that.
Well, when you're taking the division, to get the secondary step of the division, the number that goes on top of the divisionary sign,
Oh, up here,
that
yeah.
what's getting factored with x plus 1?
Well, whatever I'm putting up here, I want to multiply by x plus 1 to get rid of the biggest
Right,
thing.
sorry.
Yeah, so yeah, like this x squared, I put that there because I have an x cubed. Well, I have a minus x cubed, so I do minus x squared times x plus 1 gives me that
Gives us a minus negative.
minus x cubed minus x squared,
Okay,
which when I take the difference, I get that out, yeah. Okay, so this is the division algorithm. There's a theorem that I should tell you guys about, and the theorem is this.
Mind if I take a drink real quick?
Go for it, Michael. The remainder theorem says this. The remainder of f of x divided by x minus c is equal to f of c. So let me explain to you why that's true in terms of the division algorithm. So what's the division algorithm say? It says that we have, if we take f of x, right, and we divide by x minus c, well, that's equal to p of x plus the remainder. divided by x minus c. Now, why do I know that the remainder is just a constant in this case? Can you guys explain that to me? Why would the remainder just be a constant here? How do we define the remainder? The remainder has a degree what? Smaller than? Smaller than the divisor. So if the divisor is degree 1, that means the remainder has to be a constant. Remainder has to be a constant. Like it was in example 1 here. It was 4, right? So you guys, while I'm moving the camera, why don't you take that equation I wrote down there and solve for f of x? What do you get? F of x equals to what? Multiply the equation by x minus c, okay? Multiply the equation by x minus c. What do we get? So we get p of x times x minus c plus r, right? Okay? Now what happens if we evaluate this formula, plug in c? What happens? Plug in x equals to c. We get f of c is equal to p of c times c minus c. What's c minus? What's c minus c though? This is 0, right? So this formula just becomes r. So there you have it. That's the remainder theorem. Let's look at the remainder theorem for example 1. So remark, if we look at f of x equals to x to the 4th plus 3, then what is f of minus 1 equal to? What's minus 1 to the, yes, Michael?
4.
4, yes, that's right. And what is 4?
The remainder.
It is exactly the remainder. That's not an accident, right? Okay. So let's look at another example. Example 2. So essentially, guys, a corollary is like a really closely related result. Is what's a corollary, and so a corollary to this theorem is essentially the factor theorem. What did the factor theorem say?
Let me think. The factor theorem states complete the
No, not, well, I mean, sometimes we complete the square. Factor theorem just says this. It says f of x is equal to x minus c times g of x only if f of c is equal to 0. This is the factor theorem. It says that there's a one-to-one correspondence between the zeros of your polynomial and the factors. So if you look at the remainder theorem, it's almost the same thing, right? Because if the remainder is 0, what does that mean? If the remainder is 0 upon division by x minus c, that means that x minus c is a factor. But if the remainder is 0 by the remainder theorem, it means that f of c is equal to 0. So that's pretty much it. Let's see here. So let me look at an example. I'm trying to find a good one here on my sheet. I don't think I posted this yet. You guys should remind me to post my... I'll have to make up an example. Give me a second here. All right, so here we go. F of x equal to x to the 4th plus, excuse me, 3x cubed. All right, plus 4 plus 2x squared plus 12x minus 10. All right. let's go ahead and try to work out dividing this. Let's calculate how to divide this by x squared plus 4. Let's do that, see what happens for us, okay? See what we get. Okay, so I'll start us out. We've got x to the 4th plus 3x cubed plus 2x squared plus 12x minus 10. And I'm dividing x squared plus 4 into this. All right. So you guys get me started. What do I start with here? X squared. All right. Then what? That gives me x to the 4th. Let me be careful to write the plus 4x squared over here. Keep things together. All right. I subtract. What do I get? I get 3x cubed minus 2x squared plus 12x minus 10. All right, now I've got a 3x cubed. How do I get rid of that? Plus what? Plus 3x? Yeah. 3x cubed plus 12x. We subtract. What are we left with? Minus 2x squared, minus 10 apparently. And let's see here. What's my next move here? Minus 2? All right. Wonderful. That gives me minus 2x squared minus 8. And what happens here? Looks like we get a remainder of
12.
12. Not quite. Try again.
Oh, sorry.
What's that? 2? Yeah.
Oh.
Minus 2, right?
Minus 2. My mistake.
It's okay. Now, what does this all mean? This means that we can write f of x as equal to x to the x squared plus 4
X squared plus 4
times my x squared plus 3x
times
minus 2 minus 2. So is x squared plus 4 a factor?
no,
Not at all,
because of the remainder.
right? However, here's something interesting. You can use this formula, right? Let me underline it. So what would the zeros of this be? When x is equal to what or what?
0 when x equals to
Yes, Michael?
0. 4.
No. If we said x squared plus 4 equals to 0, that gives us x squared is minus 4, which gives us x is plus or minus the square root of minus 4. In other words, the plus or minus 2i. Plus or minus 2i are the zeros. Okay, so this formula is still interesting in that regard because if we evaluate this at 2i, something interesting happens. Check this out. So what happens when you plug in 2i into this? I'm just writing it out, but I'm being dumb because I don't really need to write. Most of what I'm writing, I don't really need to write. Why? What did we just get done saying? We just got done saying x squared plus 4 is equal to 0 when x is plus or minus 2i, right?
4i.
So this right here is 0, right? That's 0. That makes, I don't care what this is. 0 times it is what?
0.
0. And so the answer here is?
Negative 2.
-2. That's right. There's a problem like this in your homework. I have a part A and a part B, and the point of part B is to plug in the complex root that corresponds to the quadratic factor, right? Like, I think in your homework it's x squared plus 6x plus 10, right? But if you complete the square on that, you'll have like minus 3 plus or minus I as your zeros in the homework problem.
Oh, it's a problem 63?
Problem 63. Don't tell them that. They need to... That's fine, Michael. Yes,
Is it
problem...
about future problems?
Yeah, I'm talking about 62B, actually.
Oh.
Yeah. Okay, so, listen, we could keep doing long division, but I think you either understand me or you're bored with it at the moment, right?
Yep.
Okay, I don't know how to interpret that, but I'll allow it. So let us talk more about other kinds of problems with polynomials. So like we still need to talk more about how to construct polynomials of a particular type, and also more importantly, how to graph them. All right, so let's get into that. How to graph and construct polynomials. Okay, so one of the first things I need to talk about that we haven't quite talked about yet is the idea of multiplicity, which is just a fancy word for something being repeated. All right. That's kind of funny. That was very meta, Michael. Very meta. So something being repeated, yes. So multiplicity of a factor is like how many times you have it in a row. So let me just show you. It's best to show you by example. So like example 3, if I had f of x equal to x minus 1 times x minus 2 to the 4th power times x minus 3 squared, let's just stick with that, all right? Then this has 3 distinct factors, right? It has the factor x minus 1, it has the factor x minus 2, it has the factor x minus 3.
Zeros are 1, 2, and 3.
That is true. The zeros of f are respectively 1, 2, and 3. That's true. The roots of this polynomial are 1, 2, and 3. But here we have the multiplicity of x minus 1 is 1. The multiplicity of x minus 2 is 4.
Oh.
The multiplicity of x minus 3
It's 9.
is 2. Good guess, though. So the multiplicity is just the number of times the factor is repeated, okay? The number of times the factor is repeated.
I get it.
Now, you guys remember the multiplicity we've talked about multiplicity before, right? With our sign flip theorem, remember? So multiplicity has a lot to do with how it changes from plus to minus. So let me use this language to give you an example. So here's an example. Construct a polynomial of least degree, all right, who has 0 of c equals to 4 with multiplicity 3 and factor x minus 1 with multiplicity 2. We'll stop right there, okay? So I've just extended the notation, extended the concept of multiplicity to extend to like the 0 itself, right? Like I said the multiplicity of x minus 1 is 1. So this would mean that the root 1 has multiplicity 1. And we'll likewise say the root or 0 of 2 has multiplicity 4. And here the root 3 has multiplicity 2. By root, I use the word root and 0 are synonymous. Like, so f of c is equal to 0 means that c is a 0 or root of f of x, okay? So that's the language I'm using here. A 0 is something that when you plug it into the function, it makes it 0. We also call that a root of the function. And I'll use both terms. I forget which one I'm using sometimes, okay? But anyway, so can you guys tell me a formula? What do I want for my formula here, for example 4? Yes, Michael?
X minus 4.
X minus 4, all right.
G of x.
Well, x minus 4 to what power?
X minus 4 to the third power.
Very good, to the third power. And then what else do we got? X minus 1 what?
X minus 1 squared.
Squared, yep. Now, that's the least degree that you can have with all this data, right? You can't take away any of those and still have multiplicity 3 root or the multiplicity 2 root, right? Now, I could multiply this by something else and I'd still have, you know, a 0 of multiplicity 3 at c equal to 4 and an x minus 1 factor with multiplicity 2, right? I could multiply this by other things, but if I want the least degree, the smallest degree one, then this is it. Now, I could do something else, right? What could I do? What if I told you also the y-intercept is at 100. Now, would this have a y-intercept of 100? I don't think so. If I plug in 0, I get 4 cubed times 1, which is like 6. Yeah, negative 4 cubed, that's right. So what I should do here, guys, is recognize that we can multiply our answer.
Sorry.
We can multiply our answer by a non-zero constant. I usually put an a out front. I can have whatever a I want here, right? And so if the y-intercept is 100, well, that's going to be equal to f of 0, right? And that, in this case, that would be a times minus 4 cubed times minus 1 squared, also known as minus 64a. So what's a equal to? Apparently, minus 100 over 64. Right? Which we could simplify, but I don't really care. The point is that the polynomial made to order here would just be f of x is equal to minus 100 over 64 times x minus 4 cubed times x minus 1 squared. Okay, that's how we can construct a polynomial that has, you know, the 0 of multiplicity 3 that we want and a factor with multiplicity 2 and the y-intercept that we so desire, right? So this is kind of like Build-A-Bear, right? But with polynomials. Does that make it cuter? No?
Yeah.
Or just
Kind of like that.
kind of like that, just like a waste of time and money. But no. Sorry, we all love Build-A-Bear. What am I talking about? Uh-oh, have I offended you?
Oh, no.
Okay, just checking. I don't know. I mean, some people Build-A-Bear is very serious business, you know? I mean, I don't know. Example, let's see here. Example 5. Example 5. How about this? find f of x such that f of minus 2 plus 3i is equal to 0, f of I is equal to 0, and we have f of 3 equals to 0, multiplicity 2, and that should do it. Now that alone won't define it. You guys give me a y-intercept. What y-intercept do you want?
7.
Okay, so y-intercept is 7. Thank you, Michael. Interesting choice. But there we go. So, you guys, how we had a complex factor theorem. Do you guys remember the complex factor theorem? You're like, I'm trying to forget it, right? But don't do that. It's going to come back. It's already come back. So the complex factor theorem tells us exactly what we need to know for those complex zeros, right? Like, so let me just put it out here. So f of minus 2 plus 3i equals to 0. That tells me that I want an x plus 2 squared plus 9 as a factor, all right? And if you want, I can multiply that out, x squared plus 4x plus 13 as it happens. So that factor will have a 0 of minus 2 plus 3i. Now, f of I, well, that's easier. F of I equals to 0. That means that I've got x squared plus 1 as a factor. Right? And so I don't think I completed my thought here. My thought was find f of x of least degree
x least
with these properties, okay?
degree.
So my point is I'm attacking it piece by piece, all right? So like if I have those zeros as, you know, if I have these complex zeros, I have to have these particular irreducible quadratic factors, okay? And we also want 3 with multiplicity 2. What's that mean?
F3 with multiplicity 2.
This means
3 x minus 3 squared.
right, x minus 3 squared is a factor. So putting this all together, what we have, f of x is some constant a. Some constant a. Michael, you gotta stop talking, Michael. So a times x minus 3 squared times x squared plus 1 times x squared plus 4x plus 13.
X squared plus 13.
This polynomial has the desired properties, all right? It has the complex zeros that we want, and it also has a 0 of 3 with multiplicity 2. Now, what's a? Well, Michael wanted the y-intercept to be 7, right? So how do we figure out what a is? What is the y-intercept? The y-intercept is 7. So 7 is also equal to f of 0, right? That's the y-intercept is where x equal to 0. And so that's equal to a.
Equals a.
I put in 0, I get minus 3 squared times 1 times 13.
1.
And so that tells me a is actually equal to 7 divided by 9 times 13, whatever that is. 117? I don't know.
Yeah, 117.
117, all right.
Oh, hold on.
Right? And then we cancel,
Hold on.
and then we cancel the 7s and we get 1 over 11.
A equals 7.
Oh yeah, you can do that. is something you shouldn't believe because it's a lie. But this is the kind of thing that I'll feature in my math prank channel. I want to teach this class, but only with wrong calculations.
16.7.
Not sure.
But
Not
I
sure.
got 60.71.
66.
7 divided by 1, what's 7?
Yeah.
I guess she's writing in the
0. I got a different answer.
7 divided by 117. Well, I have no idea what that is in terms of a decimal approximation. I mean, I guess I could figure it out for you, but
It's not pretty decimal.
well, I guess I can't. Oh, wait a minute. Haha.
0.05982906.
You wanted to keep going. There's more.
Yes, 0.0598290, blah, blah, blah. Yes, very good. This is true. This is true. Okay, so then, the answer then for this one is a 7 over 117 times x minus 3 squared times x squared plus 1 times x squared plus 4x plus 13. All right. So there's a bunch of questions in the mission which are kind of like these two examples where I basically say, here's some data, find a polynomial which has this graph, okay, which has these properties, okay? But the other thing I ask about is to find formulas for polynomial, for like a graph of a polynomial that's given. So let's talk more about that. We haven't talked about that yet. We should talk about that. Oh, that was because 9
That was all this.
9 times 13 is 117.
Excuse me. How would you convert 3i into 9?
That's the factor theorem. That's the complex factor theorem.
So x plus 2
I wrote it with alpha and beta before. Did that answer? Somebody asked me about the 117. Did that make sense? Okay. Okay, so where was I? So let's talk about graphing.
Oh, I'm up for it.
Okay. So how do you graph a polynomial? What's the method? Number 1.
Why?
If plausible. If plausible.
Yeah.
Factor f of x completely.
Factor f of x.
Number 2, draw the sign chart for f of x.
Draw. Sign. Chart. For.
Step number 3, gather easy data to help graph. All right, so like and by easy data, I mean like if you've got the y-intercept, wonderful. If you've got another point on the graph, great, right? Anything you've got like that you can use to make the graph, we'll go for it, okay? But otherwise, that's all you need. Step 4 is graph. So let me show you how this goes.
All right, show.
All right.
Just trying my best to stay focused.
So example 6, if I go with the f of x that we just graphed, we just constructed over here. And I guess the other thing I should mention is you can look at the big picture. Big picture of the graph is important. Big picture, which is either x to the even or x to the odd,
Big
leading.
picture x even x.
So, excuse me, guys. If you think about multiplying this formula out,
Leaving
now don't do it, but if you think about multiplying this formula out, I would get what? I would get like, 7 over 117, x to the what? What's the biggest, baddest thing here? X squared times x squared gives x to the 4th. And then this multiply out gives an x squared, right? So you have x squared, x squared, x squared. X to the 6th is the biggest power possible here. And then you get stuff, I don't care what it is. And then of course we know, because Michael told us to put y-intercept at 7, there's going to be a 7 over here at the end of that. What that means is that the graph of this overall, it looks like y equals x to the 6th, right? So like even, big picture, looks like this. Odd, big picture, looks something like that, okay? If you get away from it and just look at its big picture. So the sign chart for f of x here.
I'm trying to stay focused.
That's good. So the sign chart here is very boring. In fact, I probably should find a more interesting example to start with. My bad, but we're already this far in, so let me finish it. What is the critical number for this?
Critical number is 7.
No.
What is the critical number? 7.
Say, would it be
3. Yeah, positive 3 is the only one.
3.
3.
The first one should have been negative.
Oh.
Well, the other.
Oh, the intervals.
It would be like,
Well, the other numbers are the other critical numbers are complex. They don't count here. Okay, so listen. If we put in, 0, we get 7, right? So it's positive over here. And what about the multiplicity here? Well, it's 2. So sign flip theorem says it stays positive. So the graph of this is actually kind of weird. So here's what I like to say. If you've got a root with an even multiplicity, the polynomial is going to bounce off such a point. So this bounces at 3. It's got a y-intercept of 7, which is kind of like up here. But listen, that's about all we know here, unless we're going to plug in more points. But a pretty good sketch of the graph is just something like this. That's basically it. That's all we can do with what we have to work with here. Let me look at a way more interesting example for our next example, okay? So example 7, let us suppose we have f of x is equal to x plus 4 squared times x minus 2 times x minus 3 cubed times x minus, I don't know, 6. Let me count things here. 4, 6, 7. Okay, that's good. Now here, what's the degree of f of x?
The degree of
What is the degree of my next example here? What we want to do right now, guys, is graph this. We're trying to graph the polynomial, okay? That's what we're doing. Try to sketch the graph. Oh, man, did I never move it? When did you guys move for me? Uh-oh. I wonder when I last moved the camera. Huh.
The degree
Sorry, people who aren't here.
is -4.
No, the degree is never negative. As far as I know,
4.
the degree is the largest power which is possible.
3.
Michael, if I'm talking, you shouldn't be talking, man.
So I'll shut up.
There you go. So if we put the polynomial in standard form, the leading coefficient, leading power which has non-zero coefficient.
5.
So here we have
Equals 5.
We have x squared and x cubed and x. So we have an x to the 7th here, plus stuff, okay?
equals
Um,
x7 plus
I mean, the constant term would be what? 16
16
times minus 2 times minus 3 cubed times minus 6 for what it's worth. I don't care. But there's the y-intercept. All right. So my point to you is this is order 7, which means the big picture of it is it's going to look like the odd graph over there, okay? Because the leading coefficient's negative. So I draw my sign chart. And my sign chart, I've got a minus 4, minus 2, 3 is over here, and then, I don't know, 6 is here somewhere, right?
Professor, could
Yep.
it be minus 2 or would it be 2?
Oh, I meant to put a plus. Can I change that to a plus if that's okay? No, you're fine. You're right. I'll stick. Thank you. Let me not change the problem. Yeah, but if I do that, yeah, that's fine. Thank you. Very good. Very good. The thing is, in my mind, I was making it at minus 2, which is why it was still there, even though what I wrote was, of course, at 2. Yeah, thank you. Okay, now we make the sign chart, right? So those are the critical numbers, and plug in a very large positive number. They're all positive, right? So I start with pluses here. And then the sign flip theorem says, since this has an odd multiplicity, I flip back to minus. 3 has an odd multiplicity, so I flip again to positive. 2, odd multiplicity, change back to negative. And then 4, minus 4 rather, has a even multiplicity, so we
stays negative.
Negative. That's right. And then if you do your sign chart, now before I've just said make the sign chart any old way. I don't care so much about like relative position of numbers, but when I'm graphing, I actually do try to space the numbers out like appropriate to how far they are apart in the number line, so that when I can make the graph like right under this. Let's see. So I guess 0 would be here-ish. Yeah, like here. So if that's the case, and this is just a sketch of the graph, all right? By sketch we mean that it has the features that are most important. The features that are most important for a polynomial are like its zeros and its general shape. So this has zeros at minus 4, at 2, at 3, and at 6. All right? And I can just follow the sign chart. All right, so here's how it goes. It bounces. Woohoo! At minus 4. And then this is a large negative number. I don't know what, wait, is it large? Yeah, large negative number. Somewhere like that. And it comes back here, it comes back through there, it comes back down, and then it comes back up again, and then it keeps going. And that, my friends, is how you graph a polynomial. Just like that. So the steps are factor it, draw the sign chart, and follow the sign pattern. Even factors bounce off the axis, odd factors cross the axis.
Odd
right.
factors bounce and even crosses.
Exactly backwards, yes. But
So that dip at the y-axis represents that huge y-intercept, right? Like really,
yeah, that's true. Right, yeah, wherever that is, to actually add a point, this is a sketch. To put details here, I'd have to work that out. Whatever that is.
Cool.
So anyway, we will do more of this next time, but some of you won't be here. I know. So.
There's the quiz.
Yeah, there's a quiz Wednesday, that's true.